Hello everyone, I am Deepa Khanka and with my teammate Manish Chaudhary, we will be presenting our project Predicting Taxi Trip Duration using machine learning models. Our objective is to build a machine learning model to predict taxi trip duration. We developed a complete pipeline from data cleaning to modeling, compared three models, XGBoost, Random Forest, and LSTM, and aim to identify the most accurate model while understanding the key factors that influence trip duration. This project is significant because accurate trip time prediction improves customer trust, help taxi companies optimize their operations, and can support traffic and mobility planning at a city level. We used New York City taxi trip dataset from Kaggle, which includes timestamps, GPS coordinates, passenger count, and trip duration. Since it's real-world data, it requires through cleaning and preparation before modeling. In Jupyter Notebook, this is where we perform all the data cleaning, feature engineering, pre-processing, and model training. Here is our first section. We import all the required Python libraries. Then we load the dataset. And the dataset required cleaning because it contains timestamp and coordinates values that need to be converted into usable format. So in this section, I convert the pickup and drop off column into datetime objects, remove any rows with missing values, and ensure that all numerical values are properly formatted. Next, we performed feature engineering to make the data ready for machine learning model. For example, I extracted pickup hour and day of the week from the timestamp. Here is the EDA section. We first look at the distribution of trip duration, where we saw that most trips are short with a long tail of longer trips. Then we explored pickup hours and noticed clear peaks during busy times of the day, which shows why time-based features are important. Next, we plotted pickup location, which revealed strong clustering around Manhattan and confirmed the need for a geospatial feature like distance. We also compared trip duration across different hours, showing longer and more variable trips during rush hours. Finally, the correlation matrix shows a weak linear relationship, meaning the data is highly nonlinear, which supports our choice of model like XGBoost and Random Forest. We prepare the data for modeling. We select our key features, pick up our day of week, trip distance, and passenger count with trip duration as a target. Then we build a pre-processing pipeline that scales the numerical feature in one what encodes the categorical feature. After that, we split the data into training and testing sets and feed the preprocessor only on the training data to avoid leakage. Then the transform data is now standardized for all models. We also save the preprocessor using Jobly for future use or deployment.
After pre-processing, we train three different models: XGBoost Reducer, Random Forest, and LSTM neural network. And this is a strong boosting algorithm for data and structured data. We applied grid search CV to tune the model's hyperparameter, including tree depth, loading rate, and number of estimators. After training, XGBoost achieved an RMSE of 5037 seconds. The result plot showed that most errors were centered around 0, indicating that the model was fitting the data reasonably well. On our second model, that is a Random Forest Reducer, which combines multiple distance trees to improve prediction stability using 100 trees and a maximum depth of 10. Random Forest produced an RMSE of 6164 seconds, which was higher than XGBoost. The results were also more spread out, showing that this model had more prediction error. Our third model was an LSTM neural network. Although LSTM neural network are typically used for sequential data, and we shape the dataset to make it compatible with this architecture. This model was trained for 50 epochs and loss steadily decreased. On the testset, the LSTM achieved an RMSE of 5035 seconds, making it the best performing model among three. The actual versus predicted model plots showed that many points close to the diagonal line, which indicates strong prediction accuracy. And to better understand, our tree-based models were examined for future importance. Features such as trip distance and pickup hour were the most influential in the determining trip duration. And in conclusion, the last model achieved the lowest RMSE, followed closely by the XGBoost, while Random Forest performed the weakest. This comparison highlights how different machine learning approaches behave on the same datasets. Thank you.